Move on to our next lesson on graphing logarithmic functions. So we're going to start off by graphing this exponential function, which is something that we've done before a couple of times. So we always know that with exponentials, we know 0 and 1 is going to be your point. Next to 1 is always going to be your base, so 2 in this case. And next to 2 squared gives you 4. We know if we go in the opposite direction, it's going to give you the reciprocal. So we're just not going to worry about the negative 2 for now. So let's graph this. So negative 1 1/2, 0 1, 1 2, 2 4. I'm going to connect them. This is my graph for f of x equals 2 to the power of x. So our domain here, left to right, is all real numbers. Our range starts at 0 and goes to infinity because our asymptote is at y equals 0. Okay. Is f of x 1 to 1? So does it pass the horizontal and the vertical line test? Yes, it does. Which means, yes, it has an inverse. So if we try to solve for the equation here, we have y equals 2 to the power of x, and then we switch our x and our y. We don't know yet how to solve this. So what we're learning today is the inverse of this function. The way to undo 2 to the power of something is using log base 2. So log base 2 is the inverse of 2 to the power of x. So if we're graphing this, all we're doing now is switching these points. So instead of having negative 1 1/2, we're going to have 1/2 negative 1. We're switching 0 and 1, so it's 1 0, 2 1, 4 2. So just like with all of our other inverses, we're going to switch our x and our y. So let me graph this using a different color. 1/2 negative 1, means I'm going over 1/2. 1 0, 2 1, 4 2. So now my graph is going like this. It's been flipped across the line y equals x. The domain here, my domain and my range have just switched places. So now my domain is 0 to infinity. My range is all real numbers. And my asymptote, instead of being at y equals 0, is now at x equals 0. So now I have a dotted line going up and down, like this, instead of left and right. Characteristics of this. So this one is still 1 to 1. There's an x-intercept at 1, 0, and it is increasing the entire time. Cool. Let's move on to the next page. So just a summary of all this. Our logarithmic parent function, log base b, this is our base, this little number next to the word log. That tells you what b is being raised to. So this is the inverse of b to the power of x. So whatever your base is, that's what that base is going to be. If you have y equals ln, ln tells you that this is the inverse of y equals e to the x. This is called the natural log. And then finally, if y equals log. So if there's no base, then we assume that the base is 10. So no base means that you're using a base of 10. And that's called the common log. So as we talked about with our exponential unit, all our exponential functions are going to have 0, 1, and then 1 whatever the base is. So it makes sense that our log functions are going to switch our x and our y. They're all going to have the point 1 0, and then the point b comma 1, whatever your base is. So those two just get switched around with your x's and our y's. Okay, let's do a couple of examples. If we go to number 2, so we're going to start off first with looking at our base. So we know that this is log base 3. So this is our parent function is going to be the base of 3. So using our table, we know negative 1, 0, 1, 2. So 0 is always 1. 1 is 3. 2 is 9. And this is going to be 1/3. So this is our exponential function. We know our log function is going to be switching them. 1 0, 3 1, 9 2. Okay, so my log is just switching the x and the y, and since nothing is happening to this, this is just the log function, I can graph this right away. 1 0, 3 1, 9 2. and I know that that's my graph. My asymptote has not moved, so it's still at the 0. So my asymptote is at x equals 0, which tells me that my domain goes from 0 to infinity. My range is all real numbers. Okay, let's look at a little bit trickier of an example. So we look at number 3 now. So we're starting off with this base. So my base is 2. So if my base is 2, the numbers I'm using are -1, 1/2, 0, 1, 1, 2, 2, and 4. So to draw the parent function for log base 2, I'm just going to switch them. So now 1/2, -1, 1, 0, 2, 1, 4, 2. So this is my parent function. This is what I'm going to start off with. 1, 0, 2, 1, 4, 2. Now there's a couple things that are happening to this function. So I have a negative here. It's negative on the outside, means it's affecting my y, which means it's an x-axis reflection. I also am moving it to the right 2 and up 4. Okay, so I'm going to do the reflection first. Here's my x-axis. So I'm going to reflect it across the x-axis. So this one doesn't change. This one moves down here. This one moves over here. And then I'm going to move all my points to the right 2 and up 4. So this point moves right 2, up 4, 2, 3, 4. Right 2, up 4. Right 2, up 4. So this is my final graph. And since it's moved to the right 2, I know that my asymptote is also moved to the right 2. So my asymptote is now at x is equal to 2, which means that my domain goes from 2 to infinity. My range is all real numbers, as usual. Okay, let's move on to our next one. So for number 4, because this is ln, I know that this is a base of e. So I'm going to start off with my -1, 0, 1, 2, parent function for e. So it's always 1 next to 0. Next to 1 this time for e is 2.7. This is 7.4, and this is 0.4. So to find my parent function for ln, I'm now going to switch all of them. 1, 0, 2.71, 7.42. This is my parent function. So I'm going to graph this. I have 1, 0, 2.71, and 7.42. So this is my parent function. And the only thing that's happened to this is this -3, which is moving down 3 since it's on the outside. So all my points just move down 3. 1, 2, 3. 1, 2, 3. And I'm going to connect them all. Still have the same asymptote, it hasn't moved. So I have my asymptote at x equals 0, which means my domain goes from 0 to infinity. My range is all real numbers. Okay, last problem. So for this problem, let's first rewrite. We know this negative x plus 5. I'm going to rewrite as negative x minus 5. So this is 3 log. So see how there's no base here. If there's no base here, this means I'm going to use a base of 10. So my numbers here, I know 0 is always next to 1. 1 is going to be next to 10. 2 is going to be 10 squared, which is 100. And this is negative 110. So for my log base 10, I'm just going to switch my x and my y. 1, 0, 10, 1, 100, 1. So when I'm plotting this for my parent function, I'm only going to see 1, 0 and 10, 1. The rest of them are going to be off my graph. So very steep graph. Okay, so what's happened here? So I have a 3 on the outside, which means I'm multiplying all my y's by 3. So if I multiply all my y's by 3, this point stays the same. 1 multiplied by 3 moves it up to 3, so this is my new point. And then I also am, this negative x means I'm flipping this across the y-axis. So if I flip it across the y-axis, instead of being at 10, 3, it's now going to be over here at 10, negative 3. Or negative 10, 3. This one's also going to flip over to right here. So, y-axis reflection. Finally, this minus 5 means I'm moving everything to the right 5. So all these points move 1, 2, 3, 4, 5 to the right. This one moves 1, 2, 3, 4, 5 to the right. And my asymptote also moves 5 to the right. So here's my new asymptote. I'm going to connect these 2 points. That's my function. Range is all real numbers. My asymptote is at x is equal to 5. And this is the first time it's pointing in the negative direction. So my domain actually goes from negative infinity to 5. And that's my answer.